Okay, a very good morning, everybody. Thanks all of you for coming either in person here in the auditorium or online. Welcome to HZDR. If you're on the premises, welcome to our Zoom here. I hope all of you are fit for the day. There will be a lot of work, but a very interesting day lies ahead, and I'm very happy that all of you joined this morning. I first want to thank all the organizers behind this workshop. There's Tapish, there's René, there's Mehmet, there's Julian, there's Richard, there's Simeon, there is Franz, there's many students helping here, there's Klaus. So there are quite a few people who have been making this happen in the last few weeks. It's a lot of work to get all the slides done, to get the material in such a way that you can easily follow us. One of the things that I wanted to say right at the beginning, before I introduce you to what we're doing here at Helmholtz-Zentrum Dresden-Rossendorf, is that we will not use the whole full hour until the coffee break with the introductory presentation, because some of you could not join the login session yesterday. So we want to give you the opportunity, if you haven't logged into Lumi yet, so if you haven't checked whether you can access the system and so on, that we will still take some of the time before the alpaca session starts to help you get on the system. Whether you are here on the premises or online, please raise your hand. Then after the presentation, I will remind you again, if you still do not have access to Lumi, if you're still struggling with getting access, raise your hand. We want to get you on the system before everything starts, so you can follow the workshop and actually do all the little exercises that you will do today. So without further ado, welcome again to Helmholtz-Zentrum Dresden-Rossendorf. My name is Michael Bussmann, and I'm going to guide you through in the next 20 minutes, half an hour, on what we're doing here in terms of laser-plasma interaction, specifically laser-plasma acceleration, but also going a bit beyond that. And yeah, let's just start. So with our code PIConGPU, which is one of our main working horses here for laser plasma simulation at Rossendorf, I think we have now been working on this for almost 15 years. So it has been taking some time to get the code where it is right now, and a lot of students, from master students to bachelor students, student interns, but also PhD students and postdocs and research software engineers have been working on this code for now almost 15 years, as said. And it's one of the main requisites, one of the main assets we have here at HZDR to study laser plasma interaction. But it's by far not the only one, and it's by far not the most expensive one and the most complex one. One of the very nice things we have here at HZDR is that we have several facilities to actually study laser plasma interaction in detail in experiment. The two most prominent ones here on the campus are Draco and Penelope. Both of them are petawatt class lasers. So they are pulsed lasers. They produce a very short pulse. Draco produces pulses on the order of maybe 20 to 30 femtoseconds, while Penelope will go to 150 femtoseconds. And both have, in that short amount of time, produce light of very high intensity, actually such high intensity that matter does not just get ionized, but the electrons in the matter get accelerated to relativistic energies pretty quickly. And so the overall power that is in such a single pulse is a petawatt. The energy in each pulse is not that big. For Draco, it's about 30 joule. For Penelope, it's about 150 joule. But this is still a lot of energy if you put it into a piece of matter in a very short amount of time. And usually you focus very tightly on the order of a few micron, the laser on a piece of matter. And this creates very strong fields, high pressures, high magnetic fields, high electric fields. And the energy of the laser is converted into very high temperatures. And so we can study matter under extreme conditions. And the experiments we can do here in Dresden are complemented by experiments we can also do at the Helmholtz International Beamline for Extreme Fields at the European XFEL, which is located in Schenefeld at Hamburg, near Hamburg, where they have a huge X-ray free electron laser that can probe matter at atomic scales. And HZDR has put an end station there together with its partners. And this end station is called the Helmholtz International Beamline for Extreme Fields, where we again have a high power laser, but also a high energy laser system to really create these extreme matter states of matter, and use the X-ray free electron laser to probe it. Quite recently, there's a development that we will hopefully very near in the future also have a scientific institute looking at all these different states of high energy density matter. This is why it's called the High Energy Density Institute. And it will focus not just on the fundamental aspects, but also on applications, for example, towards fusion. And so what we really have with PIConGPU and many other tools, actually many other simulation tools as well, together with the experiments, we have a real wonderful ecosystem of experimental capabilities and simulation capabilities to study matter under extreme conditions and its applications. And one of the applications we have been working here in Rossendorf for quite some while is to build very compact accelerators for particles. Usually accelerators have a certain size. The reason for this is mainly that the accelerating fields need to be produced without creating fields that actually destroy the vessels the fields are confined in. So usually you have some form of metal tank where you find an accelerating field. And if this becomes too big, actually it can even start to ionize the inner wall of these vessels which contain these accelerating fields. So you have an intrinsic natural end in how high you can make these fields usually in an accelerator. So accelerators are still pretty big. There's a lot of work on making them more compact, and one of these is to actually do what's happening anyways, create a plasma, so fully destroy the matter, and then use the charge differences between the electrons and the ions in matter to create really, really strong acceleration fields. And one of the things that we're doing here, where Dresden is really one of the leading institutions in the world, is laser proton or laser ion acceleration. And one of the very recent experiments we have been doing here quite a lot is using a target that is actually very simple. It's not simple to create, but its constituents are very simple. It's just hydrogen, but it's not hydrogen as a gas. It's hydrogen ice. It's cryogenic hydrogen. So the hydrogen is cooled down, and then you get basically a cryogenic jet coming out of the production apparatus for this hydrogen jet. And it looks like a continuous stream, more or less, like a cylindric jet. And the laser shoots on that jet. And when it shoots on that jet, first of all, it ionizes that jet, creates a plasma, then moves the electrons. It does normally not move the ions very much. And by this creates a charge separation between the electrons and the ions. And there are very different effects and dynamics happening on a very short time scale, usually below a picosecond, that then finally determine the energy of the particles coming out. And the energy of the electrons and the energy of the ions that comes out of this is locked to each other, and depending on which acceleration mechanism we are studying, we can go to very high ion energies. So here you see still the 80 MeV protons, but we have been seeing up to 150 MeV and even higher energies here at Dresden now, which happens on a very short length scale. So this jet is a few 10 microns usually thick, and the pulses, as we have said, are usually 30 femtoseconds. So the actual place where the acceleration happens is very small, and the time on which the acceleration is happening is also very short. However, the laser system is still big, so there's no miniaturization there yet, but we're working also on more compact and more energy efficient systems. And here you see one of the first PIConGPU simulations on this, and one of the things you will immediately see is this produces a very high frame rate, but still has a lot of detail, a lot of complexity. And the reason for this is that one of the tools we have been developing with Alpaca in mind is actually an in-situ visualization called ISAC that can take all the data created in the simulation and visualize it live and create a video out of it with which you can interact. The same thing you see here. This is the other way we are accelerating particles. This is a laser beam going into a gas, actually. And the way we build an accelerator here is called a laser wake field accelerator. You see a similar setup here. It's a very tiny gas cell actually, or usually it's also a nozzle or something else that you can use where the laser goes in, and it creates basically inside the plasma a space behind the laser pulse that is void of electrons, because the laser works like a snowplow in the gas that pushes away all the electrons that it first created via ionization and leaves a almost empty cavity behind the laser pulse that is now traversing at almost the speed of light through the plasma. And you see the pulse here in yellow and red, while you see the electrons in different views behind the electron density in different views behind the laser pulse. And you can play with it, and that's a very nice tool that is fully written in Alpaca. It's actually a software renderer running in parallel to PIConGPU, and so we can visualize a large amount of data that we never store anywhere, that we never copy anywhere, but that we just visualize, and by this we can study directly the dynamics of these laser plasma accelerators at very high detail. And all these dots you see are actually particles. So if you're familiar with PIC, you see how many particles actually there are, and we can resolve each of them and look at them. One of the critical things that we need to do is to actually make the quality of these beams better. And here's a setup that Richard Pausch and Ari Irman and others worked a lot with on developing a two-staged approach, where in the first so-called laser wake field accelerator stage, or LWFA stage, we created an electron beam just the way I showed it to you right now, with a laser beam going through the plasma, creating this bubble, this area empty of electrons right behind the laser pulse, in which then some of the electrons get injected and follow the laser. And so this is how you create a very intense laser pulse with a lot of charge in, but the quality usually isn't that nice. So if you want to use this, for example, for creating a radiation source, you want to have a better quality electron beam. And the way you do this is by blocking the laser and just letting those initially accelerated electrons through. And because they also have an electric field similar to the laser pulse, they create a similar structure when they're going through the second part of the plasma. So there's another plasma after this first blocking foil. And now they again create such a bubble in which again another electron bunch is injected. But this time, as you see, it has much nicer properties in terms of size. And what you just saw was really a full-scale simulation of that. That was the first full-scale simulation of a two nozzle staged laser plasma accelerator. And if you get this nice quality, you can actually use it for applications. One of the dream applications we have in the field is to create very compact free electron lasers, because usually the accelerators for free electron lasers that accelerate the particles, the electrons that are then used, are of kilometer size. Now our accelerators of a few 10 centimeters size, which is very nice. But the quality isn't there yet. So we really have to work on the quality. However, the quality is already good enough that you see the onset of FEL operation in these machines. It's not yet there in comparison to existing free electron lasers in terms of brilliance or anything or operation, but we have demonstrated that this is actually feasible, and now we have to work further on the beam quality to get things going and to really have ultra compact FELs that fit in a mid-sized laboratory. That would be a game changer, because the last large-scale free electron laser facilities are hugely overbooked. Everybody wants to use them for material science, for bioscience, for energy research, for everything. They're very interesting, but since there are very few on the planet, they're not easy to use usually, and you have to be very good and very lucky to use one of them, and it would be nice to have more of them. One of the challenges is here to actually also scale these accelerators to higher energy. We are usually now at the 10 GeV to few GeV or sometimes several hundred MeV ranges, depending on how large your plasma is and how strong your laser is. But ultimately, we will have to scale this. And one of the things that was developed here, mainly by Alexander Debus, Klaus Steiniger, and others, to really scale this, is traveling wave electron acceleration. And the idea is not to shoot a single laser pulse in there, but two overlapping pulses that in their interference region create something that very much looks like a standard laser pulse. But the nice thing is the laser pulses do not travel through the plasma, but they come from the side. So at each interaction of the two very elongated laser pulses, you have a high quality laser pulse that drives the wake you have been seeing, and it never deteriorates. Standard thing is when a laser pulse goes through a plasma, it interacts with the plasma and gets deteriorated in quality, and this deteriorates in return the quality of the electron beam. Now we can always replenish the quality of the laser pulse with which we are driving the accelerator, and we can also stage this, because we're coming from the side. We can always set a new module, new acceleration module up to the next part, and we just come from the side. It would be very hard to do this with two lasers that have to go through the pipe alongside the accelerator, because somehow you would have to bring the second laser pulse in from the side, and then it should go straight. It's very hard to bend light. When it comes from the side and then it has to go straight, it's very hard to bend light. But here, this is a possibility. If you come from the side anyways, you are very happy to create a situation that you can stage, that is stageable, and we're going to investigate this further, how far we can take this in the next couple of years. The final application, and I already told you about this, is the Helmholtz International Beamline for Extreme Fields, where we use scattering techniques like small angle X-ray scattering, wide angle X-ray scattering, phase contrast in imaging, and so on, to really image matter under extreme conditions at the atomic scale, both in time and length. And here's one of the first experiments that we had done here. By the way, you see, depending on what interaction you have, you see a laser beam impinging on the left. The laser beam is not shown, but it creates different instabilities. Studying instabilities are at the core of some of the most important applications, like, for example, laser fusion, where instabilities are actually hindering the ignition of the plasma to be very homogeneous, and thus we're losing a lot of energy in current experiments. And if we can study the creation of instabilities at an atomic time and length scale, that's a big game changer. And we can do this here, and you actually see, depending on which instability you are looking at, you see very different scattering pictures, which you see below. And these ones are created by PIC simulations. And so you can directly infer from the scattering picture which kind of instability you're looking at. And that's a very important information for many applications. One of the first experiments, and this was initiated by Thomas Kluge and many others, was that you look at the surface of a target, and what you do is you structure this kind of target. Because then it very well reflects, like a grating, it very well reflects the X-ray laser, and you can see the structure of the target. Now, if you shoot with a laser on the target, this structure gets destroyed because the laser creates a plasma and gradually destroys this surface. And you see this destruction in the reflection of the X-rays. You see this in the scattering picture. And now if you record the scattering picture over time, you get a temporal resolution of very well below a picosecond. So in the femtosecond regime, and you actually get resolution down to a few 10 nanometers to really study in detail how this structure is destroyed, both in time and in space. And this is absolutely unprecedented in resolution, and we can now basically directly compare the simulation, which works on atomic scales, with the experiment that works on the atomic scales. And this again is a wonderful working together where we for the first time look very much into detail into these laser plasma interactions and try to learn a lot on how we can control them. But, and that was very nice for at least us people writing the simulations, simulations came first in terms of resolution. For a very long time, experiments were not able to resolve the time and length scales that we could see in the simulations. And that was a problem because simulations predicted very nice things that you did not necessarily see in experiments. And so, were the experiments wrong? Were the simulations wrong? Why didn't they fit? Of course, if you're writing the simulation, you always believe the simulation is right. It has to. Everything else is just problems of experiments. But that's not true, of course. It's always an interplay. You have to learn whether you forgot some effect in the simulation or whether what you actually see in experiment is what you put into the simulation. So there's a lot of things happening in parallel, and we very early saw that this will be an absolutely high performance computing challenge. So we started to write one of the first GPU accelerated PIC codes. It was mainly a student project back then with very important people like Heiko Burau, René Videra, Axel Hübel, who pushed this to new heights. We had Guido Juckeland helping with a lot of these things, and a large growing team with Richard, Klaus and others, Alex, Thomas, getting in and bringing this code to fruition. And it's still thriving, and it's still new students are coming in to add new things. And we then saw that we could really scale to the highest systems already very early. And in 2016, we reached also for the first time a fully portable code that could run everywhere, because we had another project called Alpaca, initially developed also by a master's student, that allowed us to port the code to different architectures very easily without rewriting a lot of code lines. That was a game changer, because otherwise we would have needed a large team to always adapt to the newest compute architecture. And this is why we developed Alpaca. So I already came from PIConGPU to Alpaca. And if you're interested in Alpaca and using Alpaca, you may run into the situation that you also want to deal with a lot of data, especially in simulations, but also in high rate online analysis. So once you have mastered Alpaca, so if you're taking special care to listen to the first part today of this session on the Alpaca part and master it and put it in your code, already take some time to listen to the OpenPMD part, because you will run into the problem of creating a lot of data. So we're not saying we're solving all your problems, we're giving you new ones, because once your code is fast, it will usually be able to either deal with lots of data or create lots of data. And this is why Axel Hübel, Franz Pöschl and others are working on OpenPMD, the OpenPMD ecosystem. Actually, it's a very nice thing. It's a data standard. It's not a data format. It's a self-describing metadata data standard that has an API that you can include in your code and that now connects to a rich ecosystem of data analysis tools, online streaming workflows, visualization, and so on. So once you have OpenPMD, you do not just have very high performant I/O, you have lots more. So also stay tuned with OpenPMD, even if you just wanted to start with Alpaca. The design behind this was that we basically put Alpaca and a few other libraries of the Alpaca ecosystem, which you can all find in the Alpaca GitHub, below the actual library that we usually use to do anything in PIConGPU. That's the PMAC library you see here in green. And this provides all the standards that you need to write a particle mesh code in general, not just a particle in cell code, but usually many particle mesh codes can be written with PMAC, but it's specifically nice for PIC. And so a usual PIConGPU programmer doesn't have to know Alpaca. They usually use the PMAC. There is some quirks behind that when doing it in such a way. But in general, you do not have to really work on the more tedious part of really writing Alpaca code. You can use the PMAC library and then write PIConGPU code. And on the side, we have a lot of plugins that PIConGPU uses, and one of these is the OpenPMD IO plugin that allows to do many things. So this day today you will hear on the structure of Alpaca. I will not go very well through it, but since we started with GPUs, our idea was, why not just follow the parallelization model of something like CUDA or HIP and implement it in general. And that was essentially possible, and you can now put the different levels of hierarchy on very different compute architecture, GPUs, CPUs, even now FPGAs, ARM, and other architectures. And when we first started with that on Lumi, actually it wasn't us, it was somebody else who then invited us to join them, where they made tests with different algorithms written in different libraries for performance portable computing, like Cycle or Cocos. You see them all there, OpenMP and so on. And the gold standard was CUDA HIP on that system, to really use the new GPU architecture there. And to their surprise, not to our surprise, Alpaca even was a bit better than the native application. Reason for this is mainly that the compilers understood a bit more, and there was a bit of different utilization of the GPUs. It wasn't much, but in terms of the error bar that's still associated with this, we easily arrived at native performance. And that's not much of a surprise, because Alpaca itself does not have a lot of complex functionality. It mainly replaces code with other code, and so it comes close to a native implementation. we're still trying to keep Kupla alive. This is for us a very interesting tool still. If you have existing CUDA code, it helps you to transition to Alpaca very easily in the first try. For us, it's not that relevant anymore since most of the things are done in Alpaca anyways, but it's a very nice tool if you start with the CUDA C++ code to still move forward. And if we're now looking at the largest systems in the world, like Summit and Frontier in the US, or Lumi here in Europe, you see that we're scaling quite well. So if you're scaling quite well, on the left, that should be a line. It is almost a line. And again, on the right, this should almost be flat, where you on the x-axis actually scale up to more and more GPUs or more and more nodes. And then you look on how much the relative performance changed on the right side. So it didn't change at all. You can either use 1 GPU or 10,000 GPUs, and you always use them almost to 100%. Or you use more and more GPUs, but keep your system constant, then you accelerate and accelerate and accelerate your simulation. So this is very nice. And quite recently, we also got first data on how we think this is going to work on the upcoming exascale systems here in Europe, like Jupiter. This was scalings done with different codes at the Jülich Supercomputing Center, and you see in orange there PIConGPU compared to a few of the other codes they tested. So I think we're pretty fine on the follow-up systems. And if you're now running those codes, you produce, of course, a lot of data. And that's where the second part of this workshop comes in. This is where OpenPMD comes in, which is self-describing. So it includes already its own metadata. It's pretty easy to understand. There's units and there's descriptions on what you're putting there. And it doesn't care how you finally structure that data on disk. You can choose this, or you can ignore this. You have an API that you use. And you do not even have to write to disk. You can also write to another application that then reads this. So connecting several applications just means you write to disk, you read to disk, or you directly have a pipeline between the simulation and the further analysis or visualization workflow. And if you then go from I/O, even on large-scale systems, to streaming, you gain a lot in bandwidth, because you're no longer writing to disk. Writing to disk is slow. Even the largest parallel file systems have an upper limit, but if you go over the network and do not write at all, you can stream much more data to the next step in your analysis pipeline. And so this is pretty easy with OpenPMD. And one of the things we did very recently, and Richard was pushing this a lot, and also Alexander Debus and others like Klaus were looking at this for one of the working horses we're usually looking at, which is called the Kelvin-Helmholtz instability, which is basically a interface instability between two plasma streams, where you get very nice vortices of circulating electrons. And because they're circulating and they're charged, they create radiation. And they create very characteristic radiation patterns, which in turn tell you what's actually happening in the plasma. Now, these instabilities you, for example, see in galactic jets that are shot into the surrounding plasma in space, or you see this at jets from pulsars or other objects. So what you really see here is that at the interface between a high velocity jet and a surrounding plasma, you get these kind of instabilities. And interestingly, the way these instabilities develop depends strongly on the local plasma properties. Now, if I can link the radiation coming from these instabilities back to what is actually happening in the plasma in terms of the dynamics, so how fast the electrons are oscillating and on what radius and so on, I can learn a lot on the local plasma properties, although I'm not seeing them. I'm only seeing the self-emitted radiation. And so what we need to do is basically to compute all this self-emitted radiation and see whether we can bring it in correlation with the local plasma properties. That sounds very nice, but in reality, this means we're reaching about 100 petabyte of trajectory data from a single simulation. You can store this nowhere. So this means we directly have to take this radiation and compute it in situ during the simulation, which already is a very, very big computational task. And Richard has been one of the masterminds on even making this happen. And now we're taking this and putting it in a structure that both not just reduces the particle data, which is usually the input, and gives us a good indication on a reduced indication of the particle data, but also directly correlates this particle data to radiation data. And so we are now able to train the connection between the local plasma dynamics and the emitted radiation, and then invert this. So looking now, getting an input from measured radiation to guess what the local plasma dynamics is. And this is only possible because we have something like OpenPMD, where we can now stream this huge amount of particle data into this machine learning framework that is running in parallel on the largest supercomputer. So the simulation is running, the ML framework is running, the simulation is writing the data, the ML framework is reading the data. And because we cannot store all this data, the ML framework only sees some part of the data. So it learns in transit the current state of the simulation and tries to find a longer time picture on how the evolution of the plasma is connected to the evolution of the radiation. And this is a fantastic possibility. We can now really understand how the radiation, which is one of the main observables we usually have in plasma physics, is connected directly to the microscopic plasma dynamics. And just because we have these tools. And there's a lot of need for online analysis now in plasma physics, in photon science. Everywhere we are running into the problem of no longer being able to store all the amount of wonderful data we have, but needing to have a small time window in which we try to extract as much information as possible out of the data streams we're seeing. And so we're trying to give for free some of the tools that enable us. And I hope you're staying with us for the next 2 days to look into this. For free means we're developing all of this open source. So it's free as in free beer, but also free as in free speech. We really want to have you join also these efforts to raise your voice. Let it only be by saying, I did not understand the documentation. Very, very important input. Or you could make this much easier. Very important input. Or this did not work. Very important input. Even if you do not directly suggest a solution, pointing us to something that we have not seen is already a wonderful input. But then if you want to have something, or if you find this interesting, join. You can join the team. You will be part of a community that develops this further. And maybe you can put some tiny part or some bigger part into the project that can then be used by others. And I really think that's very important. This is not a code developed just by us. This is not our code in such a way. It's a code for the community that can also be further developed by the community. And with that, I'm finished. This is one of these beautiful in situ visualization with Isaac. That was also a master thesis where we now see the temporal evolution. So not just a single time step, but several time steps happening really in live visualization, where you can again interact with all the data that you have. And you can run this in the US, and you see it as a video here. And I think having these kind of tools available is a wonderful thing. With that, I'm finished. I took a bit more than I expected. I apologize for this. And I again want to remind all of you now, either here in the auditorium or especially also online, make yourself heard now. If you haven't logged into Lumi, if you had problems logging into Lumi, test now if you can log into Lumi. Raise your voice, raise your hand, either online or here, to see whether you are on the system. Because at 10 o'clock, latest, we expect you to be on the system. We will still have a bit of coffee and cookies at 10 o'clock, but afterwards, you need to be ready for the first tasks of this hackathon. So please check now, this is your time, and report any problems to us. And there's a lot of people here in the audience that will help you. There's people online who will help you with that. And we want to hear from you. If you're silent, we take this as a thumbs up. If you want to give us a thumbs up that you made it, we're very happy. But if you're raising your hand, your voice here on Zoom or inside, we are ready to help you. So this is the first test, how interactive this is going to be in the next 3 days. Use your time with us and raise your voice. And wonderfully, I get the very first chat message here. I only uploaded my SSH key about an hour ago. Fine. So I don't think my registration is done yet. Very well. Let's have a look into this. So now the team is here to help you with these kind of things. I thank you again for participating in this workshop and hope that you have a wonderful time. And I want to thank especially all the people who made this happen here. Again, thank you very much.
Yes, please.
This is exactly perfect. Wonderful.
So